Okay,
Go
so
ahead.
it's just announcing the meeting, saying that this is a follow-up from a meeting we had in autumn last year, where this Hydra project was presented by Augusto. Now he wants to present some updates to the project and also an application of it into in a real life analysis in LHCb. So we have a second short presentation about those applications. So I think we can get started immediately, since we are already a little bit late. We can have first the recap of Hydra by Augusto, okay?
Okay.
Thanks, sir.
You're welcome. So, can you hear me while there? Okay, so I will start. Okay, this is our update of the presentation I did about 6 months ago, and I will pass a bit fast through some points because this didn't change too much, but there are some new features, new stuff that I would like to discuss with a bit more of detail. Okay, let me start. So, okay, I will make very quickly an overview of the design, the strategies and the goals, and also review the functionalities that are currently implemented and the ones that I added in the meanwhile and will be present in the next review. And as examples, I will also take the opportunity to discuss some improvements and the new features. Like, for example, the new structure of the arrays container and some numerical integration, new routines that I added, free space Monte Carlo that got a quite huge performance boost, and the interface to Minuit. So let me start just to remind you about that. This okay. Hydra is a header-only library to perform data analysis in massively parallel platforms. This is coded on top of first, and you can perform calculations using CUDA, OpenMP, and TBB compatible devices. The design of Hydra is basically a bunch of templates. It's deploy static polymorphism in order to avoid the cost of the virtual calls. There is also no function pointer declared there or used, so the stack behavior is completely predictable, which is very important for CUDA backends. And the main feature of Hydra that I find is the fact that there is no need to learn and to write explicit CUDA, OpenMP, or TBB code. You don't need actually know much about CUDA, OpenMP, and TBB, except by some abstractions to use Hydra. So you can actually reuse the same source code you wrote to compile with NVCC, GCC, and the Intel computer and wherever. You don't need even to implement the code you already written. So functionality that is currently implemented, we have generation of phase space Monte Carlo samples with any number of particles in the final state, and sequential decays, weighted and unweighted samples are also supported. We can sample multidimensional PDFs, fitting, binning, or binary or unbinary multidimensional data sets using Minuit. You can also evaluate multidimensional functions over heterogeneous data sets. Numerical integration is also supported. There are two classes to perform Monte Carlo based integration using flat and adaptive importance sample, Vegas-like. And I added recently also some quadrature rules. In this case, Gauss-Conrad and Gens-Malik. So basically, everything interesting in Hydra happens with the help of functors. You can decorate functors in Hydra in this way, declare them in this way here to add them like the basic capabilities that are necessary to perform the calculations in Hydra. So if you have to calculate over like homogeneous data sets, you use this declaration here. But if you have, for example, to process tuples with mixed types, like you can use this constructor here. You can also like perform like almost symbolic arithmetic and composition with functors. There is a lot of implemented syntax sugar on that. And so all these expressions here in this snippet are completely legal C++ code. You can like declare new functors composing from other functors in that way and call the algorithms in Hydra to process data using that. There is also the support for C++ Lambda. Just pay attention that CUDA 8 adds support for Lambda functions in device and the host side. So you can really like have a source code that can run using Lambda functions in the GPU and in the CPU wherever time you want. And the way we can use functor lambdas in Hydra is demonstrated here. You declare in the normal C++ way your lambda, you decorate that with host device, and so you call this template functor function here wrap lambda. And now this wrapped lambda here is completely compliant with the Hydra algorithms. Data containers. Most of the Hydra algorithms can operate over any iterable C++ container from STL or First, for example. Hydra has a built-in container. It's called point vector. It's the container that is used to perform feeds, and is the container also I work all the time over that to provide optimization. So this container can hold like and represents multidimensional data points with coordinates, values, 0 in the coordinates, 0 in the values, and it's quite suitable to perform feeds and the other kinds of study. Here you can see how you can use such container. For example, it's completely obvious C++, nothing special of that. And the new container that I introduced in the infrastructure of the Hydra is the multivector. The idea of the multivector was the fact that when you really want to process, to have the capability to process data with mixed types, like tuples, you face the problem of like the etern dilemma between structure of arrays and the arrays of structures. So this container solves that things, and they also take care of some other aspects of this problem. Using this container here, you can like represent and store in memory a table with columns with different types. The table can be accessed and iterated line by line or element by element in a given column. And maybe the best way to understand how it works is looking this code here. Okay, not make this larger, but you can maybe like amplify that in your computer there. So here you see, like suppose you have like a tuple with an unsigned int, a float, and a double. No, let's call that line. It's a line in this table, in this abstract table. So like you would like to have something that should be a vector of these lines, okay? And you actually declare a type of this vector. Like you make a host vector or a device vector of these lines here, and you call that like a prototype. So you call this multi-vector, pass this type, you declare it in the way you would like it to be, in the abstract way you see that, and this creates to you these two containers here. And these containers will align all your floats, all your doubles, all your ints in contiguous positions of memory. But when you access the container, like you get back like a tuple, so you don't like lost like this human way to view like the data that is stored back. But you have also a very like how can I say efficient way to access your memory. If you are operating in systems that have a good prefetcher, for example, this would give you an advantage in your calculation. In fact, this made a very huge impact in the way the phase space generator works. And this mimics the functionalities of a normal vector and a first vector. You can push back, you can erase, you can reserve, you can do almost everything you do with a normal vector. So you can use this multi-vector, for example, to do most interesting things. In this case here, I demonstrated to you how you would store a tuple, no, or tuples of the elements in this data structure. But imagine you have an arbitrary object, and this object has some members like with different types or whatever. And you would like also to make a vector of these objects. So you can use this macro here, okay? It's called declare storable, and store your objects, the state of your objects in a multi-vector. So you have like all the states of your objects stored in a very efficient way in memory. You can access that one by one without like face the penalty of the structure array of structures access, and at the same time without lost the fact that you are dealing with this given object. Here I show to you, for example, how I deployed that in the vector for that is the for vector class in Hydra. I have basically my members are four doubles, okay? So I declare the name of the class here and the four doubles here, and so I make this prototype here because the macro will declare this type def here, desired type. So I call my vector desired type prototype, so I make my multi-vector, and after that I can push back, I can access, and I can convert on the fly like the elements of this multi-vector to a four vector. So multi-vector is deployed already in some classes, and the algorithms I deployed that in the phase space Monte Carlo, and this really eliminated a quite like a huge theft of memory that was caused by exactly the fact that being accessing a completely padded structure, array of structures. Generic multidimensional data container, I am working on that. like the point vector will be using behind the scenes this multivector to make like a more fast and the access to data. The quadrature rules use that as well. And in all the cases I tested against the old version, these presented very huge gains of performance. And another thing I didn't mention, but because it's something I'm doing not very intensively yet because I don't have time, but is the fact that I am aiming to vectorize the host part of the Hydra as well. So the multivector would be very handy to perform this vectorization when running in CPUs, multi-core CPUs. So generic function evaluation, you should be already familiar with that from the other presentation. Basically, you can pass iterators to an algorithm and a tuple or a single functor and evaluate all of them at the same time. Okay, so you can store the results in a multivector. You can store that in a vector of tuples, wherever. But you can also combine that with the ROP lambda functionality to do something like is demonstrated here in this snippet. So in this case here, I use the generator of Hydra to fill a range with angles between 0 and 2p, and after I calculate the sine and cosine for each angle, and store the result in this result container here that will be a vector of tuples. So it's possible also to perform a multidimensional PDF sampling. There is a class called random. This class uses accept to reject method to sample multidimensional PDFs, and it also provides some basic one-dimensional PDFs as well. For uniform, Gaussian, bright Wigner, I have around there in my computer also some other distributions are already implemented. I have to commit that to put all together here. And you can configure like using policies, the random number generators, and the things. The interesting about this class is the fact that this take this engages the back end where the data is stored. This understand the doses from the iterators you pass to that, where your data is, and like will you engage your GPU or CPU using TBB or OpenMP according what memory space you store the data. And so here there is some examples how to use that, like recycling the same container to fill that with different distributions. And here another example of how to use that to perform a multidimensional PDF sampling. In this case here, I am like deploying HEP Meeting to sample a sum of two-dimensional Gaussian PDFs. So you can see the result here, some tiny information here. This time I will at a certain point provide more reliable timing for that routines. I am writing some code to perform automatic performance measurement, so I can test that automatically every time I build the library. But basically you have this speed up between CPU and GPU here, you can see. And the results in both backends are completely consistent, of course. So phase space Monte Carlo. As I already told, it's possible to produce phase space Monte Carlo samples with any number of particles in the final state. The generation is managed by the phase space. class, and the storage is managed by a specialized container called events. And there is a new container, it's called chain, that will be in the next release of Hydra that can hold from the start like chains of decays. So you don't need to have too many events containers all around. So you can use policies to configure the underlying random number generator, and the events container is iterable, and so you can use that in the same way you use any other iterable container in C++ 11. And you can have a generation of weighted and unweighted samples. This supersedes completely the library I did some time ago. We presented also in HEP. Last year there is a publication circulating archive that was called MC Buster that is now used as the generator for events in GoFit. So here you have a small piece of code showing how to configure to use that, and the result is here, and some timing here. So okay, there are currently also experimental subdirectory in Hydra. There is a new version of this generator, and we can generate the same amount of events in GPUs with 10 times faster than that, like 10 times on 100 times or more faster, like in some microseconds actually, using the multi-vector container. Multidimensional numerical integration. Okay, I tried to make like a set of the popular methods to implement. So we have the plain Monte Carlo method that samples like event points evenly in the hypercube where you have your function, and integrates that and estimates the error. We have also a Vedas-like algorithm that is based in self-adaptive importance sampling. And the next release, I am putting the pieces together, we'll have also 4 new quadrature methods, the static and the self-adaptive Gauss-Conrad. I implemented these rules here from degree 15 to degree 61. The static version can be faster than adaptive version if you have to integrate smooth integrands very quickly, or if you have more complicated integrands, or you are performing a fitting with a function that is varying the shape too fast, you can use the self-adaptive. These are very similar like in the way the GSL versions work, but there is higher precision in the implementation of the rules here. And I also implemented this multidimensional gains Malik. This is a nested multidimensional rule. It's very popular. It's the one I think RuleFit use as default. It's implemented in root as a translation of the old Fortran code to C. This rule is very how can I say, convenient, because the abscissa points doesn't depend on the dimension. What depends on the dimension is the weight you are giving to each function evaluation. So you can construct the rule for each dimension you want. Basically, we have two things that limitate the applicability in the current implementations of this rule. that are around, that are like the number of function calls and also the number, the CPU time to perform all these calls. So usually people deploy these Ghens-Malik algorithms to perform integrals between 2 and 6 dimensions. Actually, the algorithms that I'm testing in Hydra and trying to optimize it a bit more are performing in a third way that we could use that to perform integrals maybe until 10 dimensions. But I still don't have like the final number for that. In all these methods, by the way, the general strategy is to prioritize the function calls. So the interface to Minuit, we can perform fits using Hydra. Hydra provides a way to put together parameters, functors, to build up, to put together integrators with functors to create PDFs. And you can, after, build a F10 using that and pass to Minuit. So basically here is the way you can declare a parameter in Hydra. You can use NumEd parameter idiom and do something like that. You can use these methods here in any order, and this will work in the same way. Or you can use the usual root fit, you pass the list of the parameters to create a parameter. These parameters overload the double conversion operator, so you can use that as against doubles as it was doubles. And this is the way you pass these parameters for the user parameters that manage also the Minuit users parameter class. So here I have some things to show that are new. Okay, this is the old or better, the current implementation in the stable repository to implement a functor that you would like to use in a fit using Hydra. So you basically have to have a constructor like here, like this one here with the parameters, and so you declare, you call the basic functor path, the class you are instantiating, implementing the type returned by the class, and the number of parameters you have in your fit is 2 here. But internally in your class, you need also to keep members of the same parameters. This is not, and you also need to register is this here, the parameters, so like Hydra and Minuit can follow them during the calculation. This is not necessary anymore. Actually, this way is a bit verbose, and it can create some confusion, bloating of code. So I found a way to do that, and in a more clear and more concise way. Now, in the new version of the Hydra, you just have to do that. Like you declare a class, and you call the base functor, and you pass like the initialized list with the same parameters you are in the constructor here. So this is all you have to do. You don't need even to keep more any member representing these parameters in the class. The basic functor will declare the parameters for you, and the parameters will be accessible through how it's called? Underscore par, and you put the index here, and you get the parameter in the order you declared here. So like your Gaussian now can be written like that, and it's quite clean syntax, and not prone to confusion, and keep also your code very concise and expressive. So okay, here just very quickly before going to finish, example, a model, we have 2 Gaussians, 1 exponential, and we are going to perform a ambient likelihood fit with that. So we have 2 plus 2 plus 1 plus 3 parameters. And I generate like 10 million events. It's a one-dimensional fit. And so you can use this code here to create your FSN and call migrad and get back the result of migrad. And this is basically the result. And we have like in black the data points, in red the fit result, and blue the shadowed blue here is events that I sampled from the PDF we just fitted. And this is the timing in a Titan Z, and also in a i7 CPU. Okay, if this is just a toy, it's just an example. We are now, Andrea will show that we are dealing with some more mundane, less academic stuff, and we also like need to keep in mind there is minuit that will manage the minimization. The point, what Hydra does is to parallelize all the function calls that are performed in the FSN, so you get a very huge speed up on that. Some testing. I tested Hydra. I have been testing in these configurations here. Sorry. In these configurations here, I showed that to the list here, but there is no space like the new configuration in LX Plus that is with GCC 4.9. In this case, I don't know why we need to suppress the flag to get like the native march in the environment there. I still am trying to understand why, but it's complaining about some like assembly instructions that are not available. And we also tested in these different cards here for CUDA. Okay, there are some LHCb analyses that are using Hydra. Andrea will present without show the data, of course. One of that analysis, the charted Kaon. He will explain better what I intend to do with that, and what is in progress now. Okay, I am implementing like sub-thread and parallelization using scenes where it's possible. I am slowly implementing a statistical model to make like statistical calculations about averages, means, things like that in parallel. It's quite clear we need also a mathematical functions model in order to speed up like the application, the usage of the library. I am also slowly writing unit tests and performing measurements for each class algorithm that matters to have that, and implementing also a generic convolution algorithm. Testing phase, this is what I would like to be in the next release, and probably will be. The multidimensional data containers that I explained, the super fast version of the free space generator. You can profile that, like you can go to my private GitHub there, where I developed Hydra, and pick up the examples and profile. You see, it can generate like in the GPUs 15 million events in 7 microseconds, very fast. Support surface space integrals. This is something I'm implementing. I need to commit. The idea here is very popular as a method to perform integrals in complicated multidimensional amplitude analysis. Instead to parameterize the model completely, but evaluate the model in terms of 4 vectors phase space event. So this routine would perform this operation like in parallel without need to implement all the stuff. Games-Malik integration and the Gauss control as well, and there are also many other improvements in the API. So you can find there is the official GitHub repository is under the multi-thread corner organization that organized to do with that things. I also have my private fork where I develop a bit more, I make experiments, is here, and this Doxygen documentation is there. It's supported by NSF, and thank you for the space and the attention here.
Thanks very much, Augusto. Before we go on to the applications, if there's any questions more on technical discussions, technical questions or comments or something to do with the design, maybe we should go through that before. So, anything concern, questions from CERN first, or okay? So from outside CERN, maybe?
This is Kyle. I was just curious if you thought some about putting some kind of Pythonic type wrapper for then constructing the computations that you're going to use doing Hydra, because it seems like in some of these, in things like TensorFlow or et cetera, you have this GPU backend or CPU backends, and you have some C++, implementation of the hardcore computation, but then there tends to be some kind of nice Pythonic layer on top. I'm just curious if maybe I'm missing it, but.
A very interesting question, because this is exactly the subject of Google Sum of Code. Me and Eduardo are submitting the request to CERN HFF organization, and some guys already applied. Our idea is to have like a bidding to Hydra, like you can use Hydra inside Python environments and glue that with the other stuff you have around, things like that. It's exactly what you told. This is already in our head. We are slowly catch up with that.
Okay, that sounds good. I think maybe we should try to coordinate a little bit, because we were doing some things kind of in a it's coming from the other side a little bit, but with a similar feeling about these kinds of, like instead of RoofIt doing something, but looking into using either, TensorFlow or some other similar backend. But so we were starting with something like that already existed and looking into, trying to do whatever, just coming from the other direction basically. So maybe maybe we should try to coordinate that.
Yeah. Okay.
That's perfectly valid as a comment. Sure.
Yeah, I'm also curious if, how much things could be mixed and matched, if you have this very efficient, implementation of like phase space integrals, that kind of thing is useful, and it's not the kind of thing that you're going to see people implementing in TensorFlow, right? So I'm curious how they can, if they're interoperable at that level, like if you had could you use the same high-level Pythonic scripting language and mix implementations of components that are in Hydra and some existing library like TensorFlow or something.
I think once we have some Python bindings for that, things like that will be possible without any major effort.
Yeah, that's why I think really it makes sense to discuss the APIs and discuss with other people as well. And that's also what I particularly like about the project, is that, as you mentioned, okay, something that can really be a core business like phase space integrations and calculations of complicated integrals and so on. These are things that are needed as meat behind many sophisticated complications. So if you can use that in an easy way with an API that is knowledgeable or flexible to use with something else, that would be extremely profitable, I think. So
yeah, great.
Absolutely, completely agree.
Okay.
Don't know if there's any more questions. Otherwise, we can go to some examples from Andrea. Yeah. Okay. So maybe we should switch to the screen, maybe.
Oh. já foi. Andrea falou.
You should be able to see actually Andrea's slides. Can you see the slides? K plus mass measurement with Hydra. Oh, not yet. Now, okay. Now I think you should really see it. The slides. K plus mass measurement with Hydra.
Okay, shall I start?
Yeah, please
All
go
right.
ahead.
First, thanks Eduardo and Augusto for inviting me to give this talk. So, as the title said, I will show you a real case, a real use case for the usage of Hydra, which is the K plus mass measurement. So let me just introduce you to the problem. I mean, this is not an academic exercise. This is a very interesting measurement. You may not know that actually there is a discrepancy between the two most precise determination of the K mass, which come from carbonic atoms. So effectively, they are measuring the K minus mass, not an average of the two or the K plus. But the reason to do that is that there is a discrepancy, and the K mass enters in many other measurements, particularly in flavor physics. And it also enters in other mass measurements, because sometimes you reconstruct final state with chaos. Now, in LHCb, what we use to perform this measurement is the decay of K plus into 3 pios, which has a large density fraction, is 5%. But as you can imagine, the chaos does not decay very often in our acceptance, so we will lose a lot simply by the fact that the chaos do not decay in LHCb. Just to give you a rough idea, I mean, a 10 GeV chaos decays on average after 80 meters, and our tracking system is 9 meters or so. So we lose a lot there. But we have a lot of chaos because we are in an hadronic environment. And what we need is to have a very large signal yield and very high purity, so that we can completely neglect the statistical uncertainty and only care about systematic studies, which of course will be the bulk of this analysis, and will be a mess. I can expect that. Now, what are the prospects of LHCb? Now, we already published an analysis on the observation, on the evidence of the sigma plus decaying into proton mu, and this analysis actually used K3 pion as a control channel. If you look at this conf note, you will see that we have in run 1, roughly 1 million events of K2 to 3 pi. Now, this was done with in a parasitic mode, because these events were triggered by something else, and we were just trying to find these events in B decays event or CHARM decays. And of course, the selection for which you get this peak was optimized for the sigma, not really for the chaos. Now, unfortunately, I cannot show you what we have in run 2 because it's still internal to LHCb, but we have a really improved trigger system in run 2. So we implemented a dedicated trigger selection, and what we have is that our efficiency for reconstructing K to 3 pi is boosted up by an order of 10 or even more. So we expect we actually have, I can say that, we have tens of millions of events. And this means that the selection can be tightened to have very high purity and still get a large signal yet. Now, when I first saw the peak, I said, okay, I need a way to process this data, and because I mean, as you can imagine, to get very precise systematic estimate, you need to do a lot of toys. It's not just fits. I mean, you can do fits in a binary way and get away with it, but you really need to generate toys in different regions of phase space. And these stories have to have a statistic which is comparable with the one we have in data. So we are again thinking about tens of millions of events for an unspecified number of toys, which would be very large. So I mean, I thought very naively about GPUs. I mean, I'm not an expert on parallel computing. I had no idea what I was doing at the time, but I knew that I should look at GPUs. So I learned about Hydra 6 months ago, thanks to Augusto, and I started playing with one of the first releases. After a few adjustments, and thanks to Augusto, I managed to run something on my GTX 1080, which was, I think, pretty new back then. It was one of the first Pascal GPUs out there. And then I was able to run all the examples and comparing the performances of between my CPU and the GTX I had at home. I mean, I was really impressed by the performance and by how easy it was to do all that. I mean, essentially I know the LHCb software, but even if you try to generate events without the event reconstruction, you still are much slower than what you could do with Hydra. So in the end, since Augusto is an LHCb, we decided to pair up and perform this analysis together. So this is my last slide. Of course, I cannot tell you much more, because I cannot show you the data. But yes. So I mean, what I found nice about Hydra is that it's relatively easy to use. I mean, I'm not an expert, and it was by following the README instruction, I was able to install it. It's very powerful, and the support is great. I don't know if the fact that I know Augusto helps, but I hope he helps everyone else as well. It runs on multiple architectures. I think also in LXPlus will run.
Run without cloud.
Yeah. So we already started working on the analysis, and we will put our code in a public GitHub repository if you want to look at it. Of course, what cannot be made public will not be made public, so do not expect to see relevant numbers. But you can see that code, of course. And that's all I have.
Thanks very much, Andrea. I understand that you can only show us some parts, but I think the more interesting one was the interesting point was to say that it's actually being used now with something a real analysis that hopefully will give a very nice measurement in LHCb. So
I mean, probably Hydra is much more powerful. I mean, can do much more powerful things than what is needed for this analysis. But this is a real use case.
In amplitude analysis, we probably show there will be other challenges that you don't have here.
Yes.
But okay, fair enough.
Yeah.
Okay. I don't know if there's any questions or curiosities from anybody on the application. There was already the comment about users and discussing for APIs and using some bits of this functionality, general functionality that is in Hydra to anybody else. So by all means, please get in touch with Augusto and Andrea for that matter. I don't know if anybody has any questions at this stage. Otherwise, we close the meeting.
One minor thing is I was just realizing that on the Diana webpage, probably this effort should be listed as, in the kind of collaborators and, partner projects and things like that, because I didn't see any list of any of these. I know it's funded sort of through a different means, but it's probably a good idea to still connect it on the Diana page somewhere.
Yeah, I'll do it in a few minutes.
Yeah. Great.
Yeah, hi. Can you hear me?
Yes.
So more of an academic question. So you said that in Hydra the stack is known at compile time. What do you mean by that?
I mean, like sometimes when you have to call function pointers, or you have to make calls to virtual members, and you try to compile a software that is coded with that structure in CUDA, the compiler will complain to you that cannot predict how large and the stack to be, because the way GPUs operate are different. No? If you have, for example, a certain code that needs more stack and is running in a CPU, the operational system will extend on demand the size of the stack that is reserved for your application. This process cannot go forever, of course. There are some limits, but even that limits are configurable in Linux, for example. But in the GPU, there is no way to do that in the runtime. So what you have to do in that case, for example, is to configure before the compilation, the size of stack your application will need to run. This make your application, for example, not scalable. If you are performing, for example, a feat or something like that, you don't know how many times you are going to call certain functions or do certain calculations or not, things like that. So, for example, this a software that you can run in one GPU cannot run in another because the stack will be different and bad things. And there are also other things. The CUDA compiler performs really huge optimizations, very strong optimizations, inlining as much as possible code. Also, in the way I write Hydra using templates, I try to perform the maximum calculations in compile time I can. So that's what I mean. Like you start your calculation and you engage the accelerator with a very well established behavior. Like so, if you have a prefetcher available, things like that, this is going to operate better. Is that I understand?
All right, thank you. So you would say it's more the stack size that has to be known at compile time, that what's in the stack.
The stack size is probably the less academic, is the most clear and the concrete example I can give to you now in this moment. If you want, I can write 2 lines of code now that will probably create problems to the CUDA compiler to realize out the stack size necessary. But it's basically, but there are also other things. Like, I mean, like your compiler would like for the compiler, like the best code would be the code that you do everything when you are compiling. You know, you finish to compile and you have your answer. Like from the compiler point of view, because he understands every calculation, everything, has control of everything that is around to be manipulated. And as much you can expose code stuff to the compiler better. And so this means to make the stack behavior very predictable.
Okay, thank you very much.
So, nothing else? I think the meeting is already a bit long since we started late as well. So if nothing else, thanks very much again for joining, and see you next time. Unless there's anything else, will happen on 24th of April. Okay, bye bye. Thanks.